Hello students, already we have discussed about this Huygens construction for the propagation of the light in a doubly refracting medium, where we have studied the 4 cases in the previous class. So now today we are going to deal with this quarter wave plate and a half wave plate. Before starting exactly to this quarter wave plate and a half wave plate, first we will know what do you mean by this retardation plates. Retardation plate are the device which is used to produce a path difference between the ordinary and a extraordinary rays. It's a device which is used to produce the path difference between the ordinary ray and an extraordinary ray. Here I mentioned O ray is an ordinary and E ray is an extraordinary ray. So there are the two types of this retardation plates. One is the quarter wave plate, another one is a half wave plate. So we are having the two different types of the retardation plates. So first we will start with this quarter wave plate. The name itself is telling quarter means 1 by 4. Okay, quarter 1 by 4. So in the quarter wave plate, let us the beam of light is incidented normally on the crystal. Crystal may be the calcite or the quartz crystal. With their face cut parallel to the optic axis, the beam will split up into the two rays. One is the ordinary, another one is an extraordinary ray. And these rays travels in a same direction but with the different velocity. Already I have shown that in the 4 cases, Huygens construction for the double refraction, we have studied that how we can incident the light normally and then obliquely. After incidenting the light normally on the crystal, the beam is going to split up into the two rays, ordinary and the extraordinary ray, and these rays will travel in the same direction but with the different velocity. When they come out of the crystal, there is a path difference introduced between them. Okay. So this path difference is going to depend upon the thickness of the plate. The path difference is going to depend upon the thickness of the plate. Now we will know what is the definition for this quarter wave plate. It defines that the plate which introduces a path difference of lambda by 4 or the phase difference of pi by 2 between the two rays is known as a quarter wave plate. Already I have mentioned the quarter itself saying that 1 by 4. So the path difference should be of a pi by 4 or the phase difference should be of path difference should be the lambda by 4 or the phase difference should be of the pi by 2. Between these two rays, we call that one as a quarter wave plate. So let us consider T be the thickness of the plate, quarter wave plate. So path difference lambda by 4, phase difference pi by 2. So T be the thickness of the quarter wave plate. Mu naught and mu e be the refractive indices of the crystal for the ordinary ray as well as for the extraordinary ray. Then their optical path is represented by mu naught into T and mu e into T. This is an optical path. The path difference introduced between the ordinary and the extraordinary ray is equivalent to mu naught into T minus mu e into T. This can be written as mu naught minus mu e into T. So in the case of the quarter wave plate, we know the path difference is lambda by 4. So previous we have left here. Here the path difference between this one is a mu naught minus mu e into T. So now we continuing this equation, we can write it here. T into mu naught minus mu e is equal to lambda by 4. The path difference is lambda by 4 in the case of the quarter wave plate. So therefore this is the thickness. So now cross multiply it, you get the thickness T is equal to lambda divided by 4 mu naught minus mu e. This is the thickness for the negative crystal, because here mu naught is greater than mu e. Similarly, we can write the thickness of this plate for the positive crystal, that is a T is equal to lambda 4 into mu e minus mu naught, because mu e is greater than a mu naught. So this is the required thickness of the plate to introduce a path difference of lambda by 4 between the ordinary and the extraordinary ray. From the above equations, it is clear that the thickness of the plate is going to depend upon the wavelength of the light used. So this is about the quarter wave plate. So next topic is our half wave plate. See here, half is a 1 by 2. Okay. So half wave plate means what here? The path difference should be of lambda by 2 or a phase difference of pi between the two rays. Two rays means ordinary and the extraordinary. Then we say it as a half wave plate. A crystal plate which introduces a path difference of lambda by 2 or the phase difference of pi between the ordinary and the extraordinary is known as a half wave plate. So in the same way, let T be the thickness of the plate, mu naught be the refractive index of the crystal for the ordinary ray, and mu e be the refractive index of the crystal for the extraordinary ray. Now their optical paths is mu naught into T and mu e into T, as we have written in an earlier case, same way. Now the path difference introduced between the ordinary and the extraordinary ray is mu naught into T minus mu e into T, which is equal to mu naught minus mu e into T. Okay, follow the same way. In the case of the half wave plate, the path difference is lambda by 2. So therefore, this should be equivalent to now lambda by 2. Okay, we have written here lambda by 2. So cross multiply it to get the thickness of the plate. So T is equal to lambda divided by 2 into mu naught minus mu e. This is for the negative crystal, because mu naught is greater than a mu e. Similarly, we will write it for the positive crystal. That is a T is equal to lambda divided by 2 mu e minus mu naught, because mu e is greater than a mu naught. And again, this is a required thickness of the plate to introduce a path difference of lambda by 2 in the case of the half wave plate. And again, these are the two wave plates we have studied. So the next, we will continue in the another topic in another slide.